All right, let's talk about the final exam. So I didn't want to re-record the video going over the Chapter 8 practice content, so I'm just going to focus on the finals that I gave in my class last semester, just for like kind of a overall sort of general review sort of thing. So before I jump into problems, I want to talk like sort of generally about what to expect on the exam. Last semester it was 8 problems. I thought that length was like about right. And as far as like content, so yeah, weird thing that happened last semester. There was like a scheduling like thing that ended up, something was messed up with the scheduling. So one of the exams was given on like Wednesday, and then one of them was given on Saturday. And so like there are like 2 different versions of the exam initially, so they needed to be like somewhat different. So that's why you'll notice that the 2 final, like the versions had like different content slightly. And there was like a version C that was given like for like a makeup exam like even later on. So the content was like pretty similar across all of them, but like had to be varied a little bit. What you should not, please do not do this. You should not be just like reviewing for the final just by doing these 3 practice exams. There absolutely will be stuff on our final that does not show up on any of these practice exams. Okay. There will be stuff that like did not show up on the exams that we did for like our exams 1, 2, and 3. There just won't. Or there will, whatever. Yeah, so you should, so my recommendation is, so everything that we talked about in the guided notes and like the practice exams that I've posted, they're all fair game for the final. So if you are only limiting yourself to like these 3 practice exams, I mean, your content knowledge is effectively going to be limited, right? Obviously. So I recommend just kind of going through the guided notes, making sure you understand everything from the guided notes, and then from there, then testing that knowledge with the practice exams. So use these practice exams not as like a primary study source, but as a way to practice your knowledge or test your knowledge to see like if there's like any gaps in the things that you were trying to learn from the guided notes or from the textbook or whatever your primary learning resource is. So let's just jump into some problems. So something like this is a very like standard problem to ask. Show that something is a fundamental set for a differential equation. To show that something is a fundamental set, there are a couple things that go into that. There are 2 things. One, so if we call these x1 and x2, let's show that each x sub I satisfies the linear system here. This should say linear system, but whatever. dxi dt equals a times xi. So we have like a left-hand side and a right-hand side of the equation. So we plug x sub I into the left-hand side and plug it into the right-hand side so that we get the same thing. So let's do for x1, the left-hand side is equal to the derivative of x1, which is e to the t, and negative e to the t. The derivative of e to the t is just itself. Same with negative e to the t. And the right-hand side is equal to 2134 times e to the t, negative e to the t. When you do matrix multiplication, remember that you're doing each row times each column. So row 1 times column 1 would be 2 times e to the t plus 1 times negative e to the t. And then the next row, 3, 4, times that same column, 3 times e to the t plus 4 times negative e to the t. We get this. So, and then we'll just simplify these entries. 2e to the t plus 1 e times negative e to the t, that's equal to just 1 e to the t. And then 3 minus 4 is negative 1 e to the t. So this is equal to what we got with the left-hand side. So it's satisfied. Let's do x2 a little quicker. Derivative of e to the 5t, and then 3e to the 5t. Derivative of e to the 5t is 5e to the 5t. Derivative of 3 times e to the 5t is 15e to the 5t. And then 2, 1, 3, 4 times e to the 5t. 3e to the 5t. Again, we'll get 2, 1 times that column, so 2 times e to the 5t plus 1 times 3e to the 5t. And then second row, we'll get 3 times e to the 5t plus 4 times 3, right? 4 times 3, doing this row times this column. So that's 12e to the 5t. And this simplifies to, well, 2 plus 3 is 5. 3 plus 12 is 15. This is what we got from up here. So we're good. All right, so that's step 1, to show that they satisfy the linear system. Step 2 is show that they are linearly independent. And we do that by computing their Wronskian and showing that that is non-zero for all t. So the Wronskian is the determinant of the matrix that you get by just taking those original 2 vectors and just shoving them into a matrix. So e to the t, negative e to the t for the first column, and then e to the 5t, 3e to the 5t for the second column. And then we'll take the determinant of that matrix. So instead of doing the square brackets, we'll do the vertical bars to indicate that we're doing a determinant. And the determinant of this 2 by 2 matrix is this times this minus this times this. So that becomes 3e to the 5t times e to the t minus negative e to the t times e to the 5t. So let's simplify that so that we can decide whether or not that's actually equal to 0. So e to the 5t times e to the t is e to the 5 plus 1t, or e to the 6t. And then plus e to the 6t. So this is still not fully simplified. So 3 plus 1 e to the 6t is 4 e to the 6t. And e to the constant is never equal to 0. And this is true for all t. All right, so this is linearly independent. It's a linearly independent set, and it satisfies the linear system. Therefore, it is a fundamental set. All right. Finding a general solution for this linear system here. All right, so we'll call this matrix A, and then we'll compute the determinant of A minus lambda I to get our eigenvalues. So 0 minus lambda, and then 13, negative 1, and then 4 minus lambda. So this simplifies to, so 4 minus lambda times negative lambda is lambda squared minus 4 lambda, and then minus negative 13, so plus 13. So our eigenvalues would be solutions to this. So we're not going to be able to factor this in a nice, easy way. You could do like completing the square or something like that, but let's not. So negative b plus or minus the square root of b squared minus 4ac all over 2a. What's that square root? 16 minus 52 is negative 36. So negative 36 is the same as 6i. So 4 over 2 is 2, and then plus or minus 6i over 2, which is 3i. So we get 2 plus or minus 3i. Great. So let's go to our formula sheet. All right, and so this is what we're looking for. Cool. So our solution, so our fundamental set is going to consist of these two elements here. So now we just need to find our eigenvector for one of these eigenvectors, the 2 plus 3i, and then we should be good, just using the formula. So a minus 2 plus 3i times v, times the identity matrix, and then that times v is equal to 0. So we're solving that equation here, that matrix equation. All right, so a minus 2 plus 3i is just negative 2 minus 3i in the first entry, right? Because we have 0 minus this. And then our off diagonals stay the same. And then 4 minus 2 plus 3i becomes this. And let's just simplify 4 minus 2 to just positive 2. So we get positive 2 minus 3i in the bottom right. We have the vertical bar and then a column of zeros. You don't necessarily need to write this column of zeros every time if you kind of remember that it's there, but I'll just do it here just because. Now we'll do the trick of multiplying this row by the conjugate of this entry here. So negative 2 minus 3i, the conjugate is negative 2 plus 3i. We'll multiply that by row 1. So row 1 star, we just get a new row 1. All right, and so negative 2 squared is 4, and then minus 3i squared, which would be minus 9 times negative 1. So we get a double negative plus 9. And then 13 times negative 2 plus 3i. Let's just leave it like that. And then negative 1, and then 2 minus 3i. And then if we just wanted to simplify that, that would be 13. And then let's pull out a negative. So that becomes 2 minus 3i. And I'm doing that so that it becomes more obvious that this row is just negative 13 times this row. You know, this entry times negative 13 is literally this. And then this times negative 13 is just positive 13. And then move that over, bring the dot. And then I'll do 13 times row 2, add it to row 1. And then that's just going to zero out that entire row. I forgot the the column of zeros over here, but I typically don't write it anyway, so let's just leave it. Okay, so this is telling us that negative 1x plus 2 minus 3i times y is equal to 0. So our eigenvector v, we could pick x to be equal to 2 minus 3i, and then y can be equal to just 1. And then this choice will satisfy this equation here. So yeah, you can always just make x be whatever the coefficient of y is going to be, and then if you were to solve for y, y would just be the negative of the coefficient that x has. The negative of the coefficient of x right now is just -1, and then introduce another negative, double negative, +1. Okay. Yeah, so that's our eigenvector. We then want to split this up into like a real part and a complex part. This is like 1 plus 0i. So this is the vector 2, 1, and then plus I times the vector -3, 0. So this is like our u and our w. So now we can go back to this formula up here. Let's just bring it down here so it's easier to copy stuff. We're after the general solution. So this is going to be our fundamental set. So our general solution is going to be x equals c1 e to the at. What's our a and what's our b? This is like a plus bi. So a is 2 and b is 3. So e to the at is e to the 2t, and u is 2, 1, cosine of bt, b was 3, minus w, sine of bt, and then plus, I'll just continue on the next line, c2 times our second thing in the fundamental set, which is e to the 2t, times w, cosine of 3t, plus u sine of 3t. And there we go. All right. Question 3. Tank is filled with 100 gallons of pure water. Johnny, who hates the taste of water, starts dumping Gatorade into the tank at a rate of 6 gallons per minute while starting. The mixture is then removed at a rate of 4 gallons per minute. If each gallon of Gatorade has 230 grams of sugar, find the formula for S of t, the amount of sugar in grams, in the tank after t minutes. There was like a little bit of confusion with how the problem was originally worded last semester, and so I actually modified the wording of this to make it like more clear what the problem was asking. And also, for some reason, I deleted the part where it said set up but do not solve an initial value problem to solve this problem. I just made it so that like you actually just have to solve it. But we'll just set it up right now because the setup is kind of the important part. All right, so ds dt, the rate of change of sugar, is going to be how fast the sugar is going into the tank minus how fast the sugar is going out of the tank. The rate at which sugar is going into the tank is going to be, well, all right, so we're dumping Gatorade in at 6 gallons per minute. And then the concentration of sugar in each gallon of Gatorade has 230 grams of sugar. So 230 grams of sugar per gallon. So these cancel, you get 6 times 230, which is 1200 plus 180, so 1380 grams of sugar per minute. This is the rate at which sugar is entering the tank. I really think that it's helpful to pay attention to the units when doing these problems, because the units kind of informs your understanding of what like these rates, like and all these numbers are sort of representing. I think that is especially useful for when you're thinking about the rate at which sugar is exiting the tank. So the mixture is being removed at 4 gallons per minute. But then what's the concentration of this this mixture that's exiting the tank, because the mixture is it's so you're not just removing 230 grams of sugar like every minute like you were for like the rate at which it's entering in, because you're pure Gatorade is entering the tank, but then Gatorade mixed with water is exiting the tank. And so after T minutes, how much sugar is in the tank? So we're looking for how many grams of sugar there are per gallon in like the well mixed solution in the tank. And so S of T just represents how much sugar is in the tank after T minutes. So we'll just say S of T grams of sugar are in the tank after T minutes. And how many gallons are in the tank after T minutes? Well, you start with 100 gallons of just water, and then that quantity of liquid goes up by 6 gallons each minute, and then goes down by 4 gallons each minute. So 100 gallons to start, and then every minute it goes up by a net of 6 minus 4, which is 2. So 100 plus 2 times how many minutes, T, that's how many gallons of liquid are going to be in the tank at time T. So this is, I'm just going to write 4S over 100 plus 2T grams per minute. So ds dt is just equal to R in minus R out. And that's our differential equation. We need an initial condition as well in order to find a unique solution to this. Our initial condition is, well, how much sugar is in the tank at a specific time. So at time T equals 0, the tank is filled with just 100 gallons of pure water. So after 0 minutes, there are 0 grams of sugar in the tank. If it said it was filled with like 50 gallons of pure water and 50 gallons of Gatorade, so it's like a 50-50 mixture at the start, then how much sugar would be in the tank at time 0? Well, then it would be like 50 gallons times 230 grams of sugar per gallon. So that would be how much sugar there is at time 0, right? So depending on like that first sentence, like how much, like what is in the tank at the start, that's going to kind of inform your initial condition. All right, question 4, determine whether the IVP below has a unique solution. If so, what is the largest possible interval of solution? Okay, so there is a theorem. Let's go find the theorem. This is from 8.1. Here we go, perfect. All right, existence of a unique solution theorem. All right, so basically it says, take some like IVP or like, like system of IVPs or whatever you want to call this. This says, as long as the entries of the matrices A of T and F of T, so this is A of T and this is F of T, just following this setup, as long as the entries of these matrices are functions that are continuous on a common interval I, and this is the important part, that they're continuous on a common interval that contains the point T0, where T0 is the point that you're plugging in here for your IVP. Then, as long as they're continuous on that common interval that contains that point, then there exists a unique solution of the initial value problem on that interval. So, if you want to know if this IVP has a unique solution, all you have to do is check that all of these 6 entries are continuous functions on the same common interval, and you need to be able to plug in that that point to that interval. So like this one over here, all of these 6 entries, the only one that's not continuous is 3 over t at t equals 0. So if you can't plug in t equals 0, the interval of solution can't contain 0. So that gives this specific problem only 2 options, either 0 to infinity or negative infinity to 0, and then you narrow it down based off of, well, which interval contains t equals 1? Well, 0 infinity does in that case, so that's why that would be the answer for this problem. Now going back to ours, 6 over t minus 5 squared, 3 over t, 1 over t plus 5, e to the t, 1, and 5. We just need to check when are those continuous. Well, the problem points are t cannot equal 5 because 6 over t minus 5 squared, can't plug in 5 there. Can't plug in 0 to 3 over t. And can't plug in negative 5 to 1 over t plus 5. So possible intervals of solution would be negative infinity to negative 5, negative 5 to 0, 0 to 5, or 5 to infinity. So any one of these intervals would be the correct, would be like a valid answer because all 6 of these functions are continuous on each of these intervals. So we just need to pick the interval that contains the point t naught equals 1, and that point, or that interval, would be 0, 5. All right, so now as far as our justification, we'll say since each entry of a of t and f of t, an alternate phrasing here is since each of 6 over t minus 5 squared, 3 over t, 1 over t plus 5, e to the t, 1, and 5, right, however you want to say that. Since each of these functions are continuous on the interval 0 to 5, and t naught equals 1 is in that interval, then there is a unique solution to the IVP on 0 to 5. So that's our interval solution. All right. Let's move on. Question 5 is on separation of variables. So this one, kind of straightforward. Whenever you're doing separation of variables, that just means separate all the x's to one side of the equation and all the y's to the other side of the equation, and then hopefully you can integrate things. So here, if you cross multiply, you can get, so divide by y squared on both sides and multiply by dx on both sides. You get 1 over y squared, which we'll write as y to the negative 2, dy is equal to x cubed dx. And then we can integrate both sides. The integral of x to the 3 is 1 over 4 x to the 4. And then we'll put the plus c over here. And then the antiderivative of y to the negative 2 is negative y to the negative 1. There's technically like a plus c prime over here, but if you just subtract it to the other side, combine it with the plus c over there, you don't really need it. So we'll just have this plus c over here be like all-encompassing. And then we'll solve for y. So negative y to the negative 1, let's multiply by negative 1 on both sides. So this is y to the negative 1. Let's write that as 1 over y is equal to negative 1/4 x to the 4 minus c. Remember, anytime that you have like a constant times c, you can like absorb that constant into the c. So let's absorb the negative into the c, just call that plus c. And then we'll take reciprocals to solve for y. So y is equal to, or let me show you the common mistake that I see first. The common mistake is people would write 1 over negative a fourth x to the 4 plus c. This is not correct because the reciprocal of this is not equal to this. Like, you can't say that like 1 over 2 plus 4 is equal to 1 over 2 plus 1 over 4. That's just not how it works. So the correct thing to do here would be to just say 1 over negative a fourth x to the 4 plus c, just all like that. All right, so this is correct. Now we have this initial condition, y of 0 equals a third. So 1/3 is equal to what we get when we plug in 0 into this. So negative a fourth times 0 to the 4th plus c. Oops. So we get 1/3 is equal to 1 over c. So c is just equal to 3. So our solution is then 1 over negative 1/4 x to the 4th plus c, which is 3. All right, and that's our solution. All right, this one right here, this is an exact solution or exact differential equation. So the hint is kind of telling you that here. So if you want to check, you don't have to like check that it's exact to like, be able to solve this problem. But if I didn't give you this hint of checking that it's exact, you would want to take the derivatives, the partial derivatives or the correct partial derivatives of each of these things here and make sure that you get the same thing for both of them. So over here, this has already been differentiated with respect to x. So now let's take it with respect to y and see what we get. Derivative of cosine of x with respect to y is just 0. Derivative of 2x times y is just 2x. Over here, we'll take the derivative with respect to x, because this dy implies that we've already taken a derivative with respect to y. So taking the derivative with respect to x, derivative of x squared is 2x. So we're getting the same thing for both of these, therefore it is exact, so that's a good sign. Remember that the whole point of exact DEs is that you're starting with some like f of x, y up here. Let's put it over here. And then if you take a derivative with respect to x, you should get cosine of x plus 2xy. And if you take a derivative with respect to y of that thing, you should get x squared plus 1. And then taking a derivative with respect to y of that thing, or with respect to x of that thing, taking a derivative with respect to x and then y versus doing y and then x, those should lead you to the same thing at the bottom here, which they do. And so now we're looking for what f of x, y is, because the solution put it in gray. So the solution to this thing is going to look like f of x, y is equal to c, because on the right-hand side, on the left-hand side of this thing, we're starting with basically derivative of f of x, y, and on the right-hand side we just have 0. So if you integrate the derivative of f of xy equals 0, that gives you the solution just f of xy equals just some constant c. And this is just going to be an implicit solution if we were to not solve for y. Remember, implicit solution means you don't need to solve for y. You can just leave it as some expression is equal to c. Explicit solution would be solve for y. So like this over here, this is an explicit solution. All right, so anyway, how do we find our f of xy? Well, we can start with either this and then integrate with respect to x to get our f of xy, or start with this and integrate with respect to y, dy, and then go from there. So let's start by integrating cosine of x plus 2xy dx to get our f of xy. Integral of cosine is sine. The integral of 2x is x squared, and then y is just a constant with respect to x. And then, it's kind of like plus c, but it's really plus a constant with respect to x. So anything that involves y's is going to be a constant with respect to x. So now we have our f of xy, and so if we were to now take a derivative of this thing with respect to y, this whole thing, that should bring us down to x squared plus 1. So if we do derivative with respect to y of f of xy, that should give us x squared plus 1. So derivative with respect to y of sine x plus x squared y plus g of y should give us that. Derivative of sine of x with respect to y, that's just 0 because it doesn't have any y's in it, it's just a constant. Derivative of x squared times y, x squared is a constant, so constant times y goes to constant, and then plus just whatever g prime of y is, gives us x squared plus 1. Let's get rid of that 0 over there. X squared plus g prime of y equals x squared plus 1. We can get rid of those x squareds, and then we can just say g prime of y is equal to 1. So then g of y is just the antiderivative of 1 with respect to y, which is just y. Yeah, okay. So f of xy is equal to sine of x plus x squared y plus y. And now to just kind of check this, if we were to take the derivative with respect to x, well, that would just go away, and then we get cosine of x plus 2xy. And if we were to do a derivative with respect to y, this would go away, and we get x squared plus derivative of y is 1, so x squared plus 1, which is that. So then our solution, our general solution, is sine of x plus x squared y plus y is equal to c, like we set up here. And our initial condition, y of 0 is equal to 1, can help us find c. So that means that x is 0 and y is equal to 1. So we plug those points in, and then we should be able to solve for c. So sine of 0 plus 0 squared times 1 plus 1, we're just replacing all of our x's with zeros and all of our y's with 1s, and then we can get our c. Sine of 0 is 0, that is also 0, c is equal to 1. So our solution is sine of x plus x squared y plus y is equal to 1. All right, cool. Let's see. 7, we have this differential equation here. So this is like a standard chapter 4 problem where we need to find the complementary solution and then the particular solution and then state the general solution. So complementary solution, we take the characteristic polynomial, lambda squared minus 2 lambda plus 1, and then we just set it equal to 0, and we'll find the roots of that just by factoring. So this factors is just lambda minus 1 squared. So lambda is equal to 1 with multiplicity 2. So our complementary solution is c1 e to the x, e to the 1x technically, and then plus c2 times x e to the 1x. So that's our complementary solution. E to the x is going to be our y1, and then x e to the x is going to be our y2, and that's going to be important for when we do variation of parameters. So technically, this is one of the ones where you could actually do without variation of parameters. Like if you wanted to do the guess and check thing, you could say y sub p is equal to a times e to the x, and then plus probably just say bx plus c just to kind of be safe. Just put like a linear thing over there just for the plus 4. But anyway, I'm specifying that we need to do variation of parameters here. But if I didn't specify that, I would probably do the guess and check method where I say this is our y sub p, then our y sub p prime is something, and then y sub p double prime, compute that, plug all that stuff into this differential equation, and then solve for a, b, and c. That would be a valid way of doing this one. Anyway, let's follow the instructions and do variation of parameters though. So we need to compute our Wronskian and then W1 and W2. Our Wronskian, let's probably move those down a little bit. Wronskian, we put y1 and y2 at the top, e to the x, and x e to the x, and then their derivatives at the bottom here. Derivative of e to the x is itself. Derivative of x e to the x, we have to do a product rule. That would give you derivative of x, which is 1, times e to the x, and then plus x times the derivative of e to the x, which is itself. So we get e to the x times this minus x e to the x times e to the x. E to the x times e to the x is e to the 2x, and then plus x e to the 2x, and then minus x times e to the x, or x e to the 2x. So these cancel, we're left with e to the 2x. W1 is when we replace column 1 with our answer column. So we put a 0 there, and then whatever our answer is at the bottom. So 6 e to the x plus 4. And then we leave our column 2 the same. So then we'll get 0 minus x e to the x times 6 e to the x plus 4. So this is negative 6x e to the 2x minus 4x e to the x. And then W2, we leave column 1 the same, and then we replace column 2 with our answer column. So this will be e to the x times 6 e to the x plus 4 minus 0 times e to the x. So this simplifies to 6 e to the 2x plus 4 e to the x, and that's our W2. Then our U1 is going to be the integral of W1 over W. W1 is negative 6x e to the 2x minus 4x e to the x. W is e to the 2x. So this simplifies as negative 6x minus 4x e to the negative x dx, because e to the x divided by e to the 2x is just e to the negative x. Cool. So then this would be negative 3x squared minus 4 times the integral of x e to the negative x dx. And I won't go through all this. The solutions are posted, but I'll just say this thing right here, you would do integration by parts on. Your u would be x, your dv would be e to the negative x, and then that should help you integrate this pretty quickly. Okay, so you get your u1 that way, and then u2 will be a little bit easier. Usually one of the two of these integrals will be a little bit harder to do. U2 is going to be 6e to the 2x plus 4e to the x divided by just w. So this becomes 6 plus 4e to the negative x, which simplifies to 6x minus 4e to the negative x. So then your particular solution ends up just being u1 y1 plus u2 y2, and then your general solution is just going to be that y sub p plus our y sub c from earlier. This was our y sub c. Remember that this was our y1, this is our y2, and then this would be, whatever this is our u1, and whatever you get over here, this would be our u2 specifically. So you just kind of throw all that stuff in, and that's going to be your general solution. All right, let's see. Video is getting a little long, so I think we'll probably just do this last problem, and that might be it. So just doing a Laplace transform over here. So anytime that you're solving something with Laplace transforms, do Laplace transform of the left-hand side. Set that equal to Laplace transform of the right-hand side. So L of y double prime, just using the formula sheet, that's equal to s squared y of s minus y of 0 times s minus y prime of 0. And then the Laplace transform of 4 times y is just 4 times the Laplace transform of y. Remember that L of y, by definition, is just equal to capital Y. Sometimes we might write like y of t transforms into capital Y of s. Lowercase for non-transformed functions, capital function or capital letter for Laplace transformed function. Laplace transform of e to the t is 1 over s minus 1. That one's straight from the table. We'll then replace y of 0 and y prime of 0 with these initial conditions. So we get s squared y of s minus y of 0, which is 1, times s, and then minus y prime of 0, which is 2. So let's factor out a y of s from both of these. We get s squared plus 4 times y of s. Let's add the negative s minus 2 to the right-hand side. So this becomes s plus 2. And then we get y of s is s plus 2 over s squared plus 4. Let's just write it as s over s squared plus 4 plus 2 over s squared plus 4. And then plus 1 over s minus 1 times s squared plus 4. We're then going to want to do L inverse of this right-hand side. L inverse of this is just going to be cosine of 2t. L inverse of this is just going to be sine of 2t. And then L inverse of this is going to be a little harder. We're going to need to split this up using partial fractions. 1 over s minus 1 times s squared plus 4 is set that equal to a over s minus 1 plus bs plus c over s squared plus 4. Has to be bs plus c because this is degree 2, this is degree 1, so you could just do a. So 1 is equal to a times s squared plus 4, and then plus bs plus c times s minus 1. So as squared plus 4a plus bs squared plus cs minus bs minus c. As squared plus bs squared. Constant terms are 4a minus c equals 1. And then our s terms are just c minus b equals 0. So we get a plus b equals 0. we get 4a minus c equals 1, and then we get c minus b equals 0. So this one over here tells us that b and c are equal. This one over here says that b is equal to negative a. So combine those facts, you get that c is equal to, since b is equal to c is equal to negative a. So if I throw that in here, this becomes 4a minus negative a, so plus a, is equal to 1. So this is 5a equals 1. A is equal to 1/5. B and C, so C is equal to negative a, and so is B because B and C are equal. So y of s is equal to this plus a over s minus 1 plus bs plus c over s squared plus 4. So y of t is L inverse of this. So L inverse of s over s squared plus 4 is cosine of 2t. L inverse of this is sine of 2t plus 1/5. L inverse of 1 over s minus 1 is e to the t. We can pull out a negative 1/5 from all of these. We could actually probably split this up as like so. So this right here, this is just 1/5 cosine of 2t. And this over here, so this one's a little trickier because, so if it were a 2 over s squared plus 4, then that would be sine of 2t. But there is not that 2 there, so if we want that 2 to be there, we can say, turn this 1/5 into a 2/10 or 1/10 times 2. And so now this is minus 1/10 of sine of 2t. All right, so that's how you do it. Yeah, and let's see. Is there anything of note from the other one that's like particularly different? Let's see, maybe that one. Yeah, the only like main differences over here is that this one over here uses an integrating factor method. So main thing I want to note with that, you always want to normalize before you do anything with the integrating factor method. So divide everything by x minus 1. And then your integrating factor is just going to be e to the integral of whatever this is. So 2 over x minus 1. So that's e to the 2 ln of x minus 1, which would simplify as just x minus 1 squared. Then you multiply both sides of the normalized thing by x minus 1 squared, and then you can reverse the product rule and then kind of proceed from there. And then let's see, this one, Newton's law of cooling states that the rate at which the temperature of the body changes is proportional to the difference between the temperature of the body and the temperature of its surroundings. So that would tell you that d capital T, d little t, the rate at which the temperature of the body changes is proportional, so it's going to be k times something. It's proportional to the difference between the temperature of the body and the temperature of its surroundings. Temperature of the body is capital T. Little t represents time. Capital T represents temperature here. Temperature of the surroundings is just the room temperature. So in that case, this is like a 70-degree room. So just K times T minus 70. This asks us to solve or set up an IVP, so we need some initial conditions as well. So this says that the the bread reaches 200 degrees Fahrenheit and then is placed in the 70-degree room. So T of 0 is 200. And then after 20 minutes, the temperature is 100. So T of 20 is equal to 100. So those are your two initial conditions for this problem. All right, we'll end it there. Thank you all for listening. Please let me know if you have any questions. Solutions to all these problems are posted on Husky CT as they normally are. Remember that you'll get this whole formula sheet. It'll be like a sheet that you can just kind of rip off for the final. And if you have any questions, please just let me know. I'll have office hours online tomorrow. So yeah, have a great day and good luck studying.